Right, question 9. We're given some information about the elements sodium, lithium and potassium. We're told they have similar properties. They're all stored in paraffin oil. A student took a small piece of sodium and added it to water. The sodium floated on the water and moved about on the surface. A lighter splint was brought near the sodium. When the reaction was over, some universal indicator was added. So this is a demonstration that I'm certain that you've seen. So question 9a, why are they stored in paraffin oil? It's only 1 mark, and the reason is because they're so reactive. They actually react with the air. Okay, they react with air or the oxygen in the air. And so we need to store them in oil to stop that from happening. You probably remember when you put it on the desk, if you cut it, first of all you see a shiny surface and then very quickly it turns dull, and that's because it's reacting with the air. Okay, question B, what would you see? So with your eyes, okay, when the lighted splint is brought near the sodium in the water, okay, well, it's producing a gas hydrogen, which comes up later actually, and that is flammable. So you're going to see a flame, and because it's sodium, that flame will actually be yellow. Okay, depending on which metal it is, depends on which color the flame is. In this case, it's going to be yellow because sodium burns with a yellow flame. Okay, question C, which gas is produced in the reaction? Well, I've just named it for you. It's hydrogen. Okay, you make hydrogen gas, okay, which is produced. Okay, and you have to fully explain how you can prove this for 3 marks. So that's just 1 mark naming the gas. Now, how can we prove we've got hydrogen? So you should remember learning gas tests, and we've got one just for hydrogen, and you have to use a lit splint, and you put it close to your hydrogen, or you put it into a tube that you've collected of hydrogen, and what you will hear is a squeaky pop if it's hydrogen. Okay. Question D, describe the color of the universal indicator before and after it's added to the trough, and explain why the color change happens after the reaction of the sodium with the water. Okay, so if we think about the color of universal indicator before we add it, when we get it in the bottle, it's green. That's the color for neutral. After it's added to the trough, okay, well, it's actually, you need to know that what it produces is an alkali. When sodium and water react together, it produces an alkali which is actually dissolved in the water, and so it will actually turn purple. Okay, or with some forms of universal indicator, it will actually turn like a dark blue color instead of purple. Okay, now, so that answers the colors, and then we've got the why the color change happens. Okay, well, it's because the product which is being produced, okay, is an alkali. Okay, it's an alkali substance. It's dissolved in the water, and it's an alkali substance. The water hasn't turned into an alkali. That's the common misconception. Okay, the alkali is just dissolved into the water. Okay. Question E, apart from a gas, so except for the gas that we named here in C, what is the chemical name of the other substance produced? Okay, well, when we react sodium and we put it into water, we make the hydrogen that we've just discussed, and then you make sodium hydroxide. Okay, and that is the alkali that we discussed here, and it's the answer to this part, sodium hydroxide. Okay, question F, how does the reactivity of cesium compare to that of sodium? Well, if you go to your periodic table and you look at the positions of these two in group 1, you'll see that cesium is below sodium. It's a couple of positions down, and hopefully you remember that as you descend group 1, the reactivity increases. And so it is actually more reactive, okay, than sodium. Okay, and lastly, question G, why do the elements sodium, lithium and potassium have similar properties? Well, if you look at their positions, you should see they're all in group 1, but that's not a why, and we've put them into group 1. You know, people decided to put them into group 1, but why do they have similar properties? Well, it's all to do with their 1 electron in their outer shell. Okay, they have 1 electron in their outer shell, and that gives them that reactivity that they have. the fact they're so reactive, and explains their patterns of reactivity. Okay, just saying they belong to group 1 isn't really enough, because there's a reason why they belong to group 1, and that's because they have that 1 electron. Okay, so you need to actually explain that in order to answer the why part.